In this presentation, we will discuss on the encoding and solving partial information games. This is a joint work with Souheib, Baarir, Potop-Butucaru, Nathalie, Sznajder, Tible, and Sebastien Tixeuil. But before going to partial information games, let me give some motivation. In our life, or they are coming more and more in our lives, we have robots, or robots-like, for example, smartwatches, IoTs, or robots vacuum cleaners that do have a common goal, usually to achieve. For example, the vacuum cleaner is to clean our house, and the smartwatches is to give the time or give some numbers about our health. In this work, we study Oblivious robots that have been discussed in the literature before, and we do consider robots that are anonymous. They do not have any identity, they do not have any memory, so they don't remember what happened before, they cannot communicate between them, they do not distinguish their left to the right, basically, and they move on a discrete ring, one step at a time, so they can move clockwise, they can move counterclockwise, so to the right or to the left. They can stay immobile if they want to, and they can be confused. So they want to move, but they don't know exactly where, so there will be a non-determinism there. And they all share the same algorithm, so they're using a distributed algorithm basically to achieve a goal. To study them, we use the Corda model that is basically a look, compute, and move. So a robot first look at the ring for the configuration where I place the other robots, then compute its movement, then after the computation it can move. And after the movement it goes back to the look phase where again it looks at the system and so on and so forth. So basically we have our example here, where we have two robots. One robot is here, and the other robot is here. They both are in the look phase, so they look at the system. They compute their next movement, that is basically this one's going clockwise and this one counterclockwise. But we do consider asynchronous system, so one robot can move and complete a phase without the other even doing one. So our robot here can move first and can even go to the next compute phase before this robot even moves. And they share the same algorithm as I was saying. And an algorithm, what it is? Before giving the definition, we first need to define a view. The view, so what happens during the look phase of the robot is the robot takes a self-centered picture of the ring. And that is what we call the view of the robot. And an algorithm is just a function that takes a view and outputs the next movement of the robot, where the exclamation point is being indecisive, so the robot wants to move but do not know where. -1 is a counterclockwise movement, 0 is the robot wanted to be immobile, and 1 is the robot wanting to move clockwise. And we have some restriction on our algorithms. First, if the view of the robot is symmetric, then the movement the robot wants to do should be 0 or indecisive. If the image of the view is indecisive, then the view of the robot should be symmetric. If the view is not symmetric, then the movement of the robot should be either moving counterclockwise, either staying immobile or moving clockwise. And the image, and lastly, the image of a view is always symmetrical to the image of a symmetric view, where the image of counterclockwise is clockwise, the movement of being immobile is immobile, and so on. The goal usually is to find an algorithm that solves an objective. So, as I was saying, all the robots have a common objectives. And in the literature, we can find some objectives. For example, gathering, which is all the robots want to gather at the same place. And once they gather at the same spot on the ring, they do not want to move anymore. the exploration stop, which is basically the robots want to explore all the spots of the ring. So each spot of the ring should be visited at least once by a robot, and then they have to stop. And we have the exploration where we want all the spots on the ring to be visited infinitely often. We can find in the literature the problem has been intensively studied. For some configurations, so the size of the ring and the number of robots, and some of the objectives I listed above, there are some algorithms that have been proposed. The problem with these algorithms, not all but some, is that they are not formally verified. And hence, from time to time, there are some bugs that are found in the proposed algorithms. So, a goal is to propose a methodology to first, if possible, to verify such algorithms. The problem is that their algorithms are complex, especially in the asynchronous phase, so it will be easier if we are able to generate automatically algorithms for the robot and propose a correct by construction fashion. So the algorithm we will propose will be proven correct because by construction it is. And if we can do that, then we are solving our problem, and we can be sure that the algorithm is working. And if we cannot find any such algorithm, so we have a proof that such algorithm doesn't exist for the configuration needed. To do that, we transform our problem into an automaton, basically. So we have a configuration. So here again, we have one robot that is here and another robot that is here. To work on them, first what we do is we numbered the spots of our ring. So 0, 1, 2, 3, 4, 5, and we select a numbering that is counterclockwise. And we also identified our robots. So we are saying that the first robot is at position 1 in the ring, and the second robot is at position 3 on the ring. We are using the that identities, but the robots do not have them, and they cannot use that. That identifiers cannot be used in the algorithm. Then this phase means that the robots, so the robot at position here, the first robot, and here the second, are on the phase ready to look compute. So they are at the first phase. They are just trying to look at the system. And the last one here is bottom, that just saved if a robot moved or not. Because if one robot never moves, we cannot ensure to satisfy the problem. Then, once an algorithm is decided, so for example here F is an algorithm that says that, well, robot 1 should go to spot 2. Then we can draw an arrow to a new state where now again we have the robot 1 at spot 1 and the robot 2 at spot 3. But now the robot at spot 1 decided to move counterclockwise, and the robot 2 at position 3 didn't do any phase yet. And since no robots moved, then they both saved at bottom. So we can build our automaton like that and have a really big automaton that represents all the possible position, all the possible algorithm that we can apply it. The thing is that some configurations are equivalent. For example, this configuration is exactly equivalent to this one. Actually, we just moved everything one spot clockwise. But for each of the robots, the view is the same, because they are always seeing the same things as if the robot is self-centered on itself. So if we consider that some configuration can be equivalent and we mark that, we have something that resembles that event actually is a partial information game, where a partial information game is an automaton where there is an initial state, or there are a lot of initial states, and there are transitions, there are edges between states that are labeled with actions. So for example, in state I1, one can take action A, and once it takes action A, there is a choice, there is another determinism that will select if it has to go to state I2 or the state I2 prime. And one thing is that both of these states are colored the same, so they are in the same observation for the robots, basically. Once the robot in state I2 or I2 prime doesn't know in which state it is, and the same for I3 prime. And there can be a final or some final states depending on the objective and the condition of the game. So to work on these partial information games that has been defined already, there are the notion of strategy. So a strategy is basically just given a sequence of states, what is the next actions to do? And for example here, if we are in states, we have a sequence of state and we rise to I2 prime, it's better to do A. But the thing is, if we don't know if we are in I2 prime or I2, we cannot know what to do. And even more specific strategies are the memoryless one. And the memoryless to consider only the state in which we are. So for example, if we're in state I2, we just consider that, and we do not consider all the states we visited before. The partial information games that have some winning conditions. So I stated that we can have some final states, and let's just call F the set of final states. We may have different winning conditions in partial information games. So for example, the reachability, which has to visit at least once a final state, the Bucci condition that has to visit infinitely often states in F, the Corbucci condition that has to visit only finitely the states in F. And we say that a strategy is winning if all paths induced by the strategy satisfy the condition we want. And one thing we proposed and proved in this paper is that for the objective of the robots, again, of gathering exploration or exploration stops, once we build our automaton that actually is a partial information game, if we found a winning strategy for that partial information game with a suitable winning condition, then we can build an algorithm for our robot, which is nice because now we can just compute a winning strategy on our partial information game. The thing is that how can we compute the memoryless winning strategies? Because that has not been done yet. To do that, we first proved that finding memoryless winning strategies in partial information games with reachability, Bucci, or Corbucci conditions is NP complete. So since now we know that the problem is NP complete, we can just encode it and encoding in SAT, giving it to a SAT solver, and then once we have an answer for the problem, then we can compute our algorithm. And if we do not have any answer for the SAT, then we know that there is no algorithm for our robot. An example of encoding of our game into a SAT formula, we're just taking a reachability condition, how we can encode reachability condition, a reachability game into a SAT formula. And first, just a notation, we say that Q1 and Q2 represents an edge between Q1 and Q2 with action A. So if in the automata that is induced by the strategy, So if the strategy picked this edge, so it will be evaluated at true, basically, and if not, it will be at false. Q1, Q2 represents the existence of a path from Q1 to Q2, and Q1, Q2 bar represent the existence, not the existence, but is evaluated at true if all paths from Q1 to Q2 are winning for reachability. And one specific thing is that we just consider that the first, so Q1 here is not winning. If Q1 is not winning, we do not necessarily have this at true, because we can always have a new an OR saying that if Q1 is at true, then everything is at true. And then our formula is here. So it's just a conjunction of all these, where the first one just says that if in a state we do take an action A, then in all the states in the same all observation set, so all the states that are in the same information set, we should have picked the same action, to respect the fact that we do not distinguish between each of these states. Also, we require to have at least exactly one action picked at each state. So if we take action A, then there is no other action B that we can pick in Q1. And the same, if there is an action B we take in Q1, then we cannot take A. That's why we have the XOR. Also, if we have an edge between Q1 and Q2, then we have a path, basically. And by induction, if we have a path up to Q2 from Q1, and we have an edge from Q2 to Q3, then there is a path from Q1 to Q3. If Q2 is not winning, is not a winning state for reachability, then we assume that there is at least one path from Q1 to Q2 that is not winning. This condition. And also if Q2 is not winning, but we know that that all paths from Q1 to Q2 are winning, then that means that there exists on all paths at least one state such that Q1 to Q3 is winning, and then we can reach Q2 from Q3. And lastly, this condition, we need to just look at the negation, where the condition, so the inside, means that a path is not winning if first we reach a path from Q0 to Q, which is not winning, and then we can loop on Q. And on the loop to Q, there is at least one path that is not winning. That is the only way that we do not have reachability. So we do not visit a state infinitely often. So when we take the negation of this formula, we have what we want. So taking a conjunction of all these formulas gives us exactly what we want. And equivalently, we can encode the others conditions into that formula as well. So as I was saying, to solve the gathering or other problems for Oblivious robots, we could have used what we just done. The problem is that the automaton we obtain suffers an important exponential blow-up. And for some open configuration, the size of the generated formula we have is too big to be considered as an input for a SAT solver. To terminate, we model Oblivious robots into partial information games, and then we can generate with our methodology correct by construction algorithms. Also, we show that there exists an algorithm for gathering and other problems if there exists a memory-less winning strategy for the constructed game. We also proved that there exists the existence of number-less winning strategy for partial information games with reachability, BUTI, or QBUTI objectives is NP-complete. So the next goal we want to achieve is to encode our problem into an SMT solver that will give us the solution without suffering the exponential blow-up in the input. So thank you for listening to me, and if you want to reach us,